So for section 11.3, we're looking at the spectroscopy data to help us identify organic compounds. Now this is part of analytical chemistry, which is looking at the analysis and what the analysis can tell us about the compound or reaction. So qualitative analysis you've been doing since Chem 1, we're just looking for making our observations to show that something happened, but it doesn't tell us anything about the amount of the substances. Quantitative analysis, that's where we start looking at the amounts of the substances, so that could be done through concentration or stoichiometry, lots of different mathematical ways. Structural analysis is what we're looking at here in section 11.3, and it tells us how the atoms are put together, what type of bonds and arrangements we have. Now there are several different techniques. We're going to focus on each technique individually. However, you can't just look at one technique to determine the compound. You tend to look at all of it together. The first one that we have, though, is mass spectrometry. This is something that we talked about in Unit 2, actually, and it's on page 67, so you might want to go back and look at that page again. But we used it in Unit 2, or Topic 2, to discuss the average atomic mass. So we had our element sample put in, we ionized it, and then it swung through the magnet and hit the detector, and depending on the mass charge ratio determined where on the detector it would hit. Now though, we're going to look at putting a compound in there, not just a single atom or a single element. So mass spectrometry can have fragmented patterns. You have to ionize it, so it removes that ion. So all of our fragments should have that positive charge. And then you should remember that the positive, lighter mass, more charge particles will deflect more in the mass spectrometer. So the more charge you have and the lighter the molecule, the more it deflects. All right, so the other thing is to remember that these particles are being collided together, so the molecule actually breaks apart. So in this picture down here, you have propanone, and we're going to break apart this into particles because of these collisions that are happening. The largest mass peak is called the parent ion. That's the particle altogether, but has a positive charge because it's been ionized. The other peaks then result from the breaking apart of that parent molecule. So let's take a look at this one on a larger scale. So here we have our parent ion at a mass of 58, and you can tell because it's the last tallest peak. And we have that positive charge because there was an electron lost, but the molecule is still all in one piece. And then what we have, the next largest peak is at 43. So if we took the masses and we subtract them, what we find is there's a mass difference of 15 grams per mole. So something with a mass of 15 then was taken off of our particle. And a mass of 15 happens to be our CH3 group. Carbon and 3 hydrogens have a mass of 15. So when you have that difference, what happened was the CH3 ion came off. So if we look down here at a mass of 15, we can actually find that. And then the rest of it left over had a mass of 43. So just by looking at how much mass was lost, we can kind of understand what was grouped together in one piece. Now these extra lines down here that are really close to the axis, so they don't have a lot of relative intensity, that's called background noise. So we don't tend to focus on every single line, we just focus in on the biggest lines. Each fragmentation is one of the products keeps the positive charge. So remember, there always has to be a positive charge. And then in section 28 of your data booklet, which is actually on page 27, it tells you what those masses lost means in terms of spectrometry. So that loss of 15 in your data booklet, it tells you means a CH3 group was lost. So here's our spectrum for ethanol. And hopefully you remember that eth means 2 carbons. And the OL part at the end of the name means that one of those carbons has a hydroxyl group on it. And then the rest of the 4 bonds for the carbon are filled with hydrogens. So this is kind of what our ethanol looks like. And if we look down here at our spectrum, we can see 1, 2, 3, 4, 5, 6, that we have our parent ion mass at a mass of 46 grams per mole, which is what the mass of ethanol is. And then if we look here at this one less, that would just mean that you had a hydrogen come off. So it could be CH3, CH2O plus. So we've lost that hydrogen attached to the hydroxyl group. And then, so remember, the heaviest mass is the parent ion. One less than that is where you just lose a hydrogen, and I know that's not in your data booklet, but hopefully we can remember that. So a question on the test might be, well, what does the mass of 31 represent? So this really big, tall structure or line here, what does that represent? So to figure that out, you have to look at the mass difference between the parent ion and that ion that you're trying to do. So if we did 46 minus 31, we get a mass loss of 15. Okay, that means if you lose a mass of 15, then you lost a CH3 group. So if I take my molecule here and I break it and I lose the CH3, then what I'm left with is the CH2OH. And remember, it's got to have a positive charge. So that is what that mass would represent. So again, you take the difference in the mass, and that tells you what piece has been lost, and then you can just take that piece off of your structure. All right, so what could have a mass of 29? So now we're going to a different line. So again, we're going to look, what's the difference between the mass of the parent ion and this line? So we would say 46 minus 29. That gives us a loss of 17. And then looking at section 28, we can see that when you lose 17, that you tend to lose the hydroxyl group. So now if I look at my structure and I take off the hydroxyl group, what do I have left? I have CH3CH2 plus, remember that positive ion. So that's what the mass at 29 could represent. It's a little easier when you're doing it this way and you have your structure and you know what to take apart. So let's look at how this type of structure can lead us, or this type of analysis can lead us to the actual structure. So here we have a molecule, the empirical formula is CH2O, and we want to know what the molecular formula is, and then give a possible structure. So we look and see what's the mass of the parent atom. Well, the mass of the parent atom is 60. So if we do 60 divided by the mass of the empirical, so carbon, 2 hydrogens, and oxygen, has a mass of 30. We have a multiple of 2. So the molecular formula then is C2H4O2. Now we just have to try and figure out how all of those atoms are bonded together. So if we look at the big lines here that we have this line right here. So if we look at the difference in the masses, 60 minus, and that's at 45, that would tell us we lost a mass of 15. And so we lost CH3. So right away we know that we have a CH3 group. Now we have to figure out what the other part looks like. So let's look at the next line. From this line to this line, we would say 60 minus 43 gives us 17. And we know that when we have a loss of 17, that means we lost a hydroxyl group. So now I know that this carbon, our second carbon, has the hydroxyl group. I know that the two carbons have to be bonded. Well, that takes up all 4 of my hydrogens. And since this carbon needs to have 4 bonds, I know the second oxygen then is double bonded. So that's kind of how you can use the mass spectrum to build your molecule.